All right. So let's look at units of measurement and precision and accuracy. So types of observations and measurements. So we make qualitative observations of reactions. Qualitative means it describes the quality of it, such as changes in color and physical state. We also make quantitative observations that involve measurements with numbers and units. By the way, the attached thing are for y'all the paper I just handed out. We'll go over this PowerPoint and take notes on it. So, a measurement always has two parts. No naked numbers. Yeah, so I got these PowerPoints through Miss Anglin, and Miss Anglin got them from some, I think, some disc that came with the books or something. It's an old PowerPoint, and it's being uploaded into a current version of Microsoft Office. The value, this is the number. A unit of measurement, this tells what you have. For example, 20 meters, 200 meters, 15 milliliters, 13.98 grams. Units are very important. I take off points. I actually will take off exactly 1 point for ever missing unit or incorrect unit. I've had a student go through a very long homework assignment that had 50 questions or 50 questions on it, and it's very simple to do, but they forgot units on everything. So they spent like an hour or two working on it, and I took off 50 points because there was units missing on everything. You'll see that like 20 questions on your homework, if you don't put units on them, it could be 20 points off just for missing units. So physical quantity, mass, the unit that is most often used is kilograms. These are the SI units of measurement. We will be slightly adjusting it. Usually it's better to use grams, but in calculations we usually always use kilograms. I might slightly change it and have you do grams instead of kilograms. These are the base units that we will be working with. Length is going to be meters. Time is going to be seconds. Temperature will be in Kelvin. Amount of substance is going to be mole. So instead, we might use centimeters also, and milliliters versus liters. From these base units, we can combine them using mathematical operations to obtain derived values. Some of these derived units will be density. Density will be in grams per milliliter. A milliliter is the same thing as a cubic centimeter. Area is meter squared. Volume will be meter cubed. Again, we'll probably be doing volume in terms of cubic centimeters, which is the same thing as a milliliter. Kilo means 1,000 of that unit. So a kilometer, sometimes called just kilometer. But kilometer, you can replace the word kilo with the word thousand. So 1 kilometer is the same thing as 1,000 meters. Centi means 100th of that unit. So 1 centimeter is 100th of a meter. Also equivalent, that means 1 meter is 100 centimeters. $1 is 100 cents. Milli means 1,000th. So 1 millimeter is 1,000th of a meter, or equivalently 1 meter is equal to 1,000 millimeters. So again, Miss England created this or used it, and she likes using a lot of mnemonics. King Henry died unexpectedly drinking chocolate milk. So to convert from one metric unit to another, you can use this mnemonic. How to convert? So here's a good device. So King Henry died unexpectedly drinking chocolate milk. So the U is going to stand for unit, or your base. So we would write, like, for meters, we put M under the unit. Liters would be under U, and grams would be it. And then we have kilograms, the K. We have hectograms, decagrams, then just grams, then decigrams, centigrams, and milligrams. So because there are two D's, the deca, we use the letter DA to separate it from deci. So 1 decagram would be equal to 10 grams. 1 hectogram would be equal to 100 grams. 1 kilogram would be equal to 1,000 grams. 1 decigram would be equal to 1/10 of a gram, or equivalently 10 decigrams is equal to 1 gram. 1 centigram is equal to 1/100th of a gram, or 100 centigrams are in 1 gram. There are 1,000 milligrams in 1 gram. So to use this, look at the problem, look at the unit that has a number on the device, put the pencil on that unit, move to the new unit, counting jumps and those in the direction of the jump, move decimal in original number the same, move decimal in original number the how's that? Move decimal in original number the same number of spaces and in the same direction. So, for example, if you want to convert 56 centimeters to millimeters, look at the unit that has a unit 56 centimeters, and on that device, put your pencil on that unit. So under centimeters, and then move decimal in original number the same number of spaces in the same direction. So we're trying to go from centimeters to millimeters, so we move it to the right 1 space. Personally, I don't use this, I just use math. So this is under centimeters. So for the C, this is under C, so we have 56 centimeters. To convert it into milliliters, we move it over by 1. So over here, 56.0 centimeters. We want to convert it from centimeters to millimeters. We move this over by 1, making it 560 millimeters. Does that make sense? We want to go from centimeters to meters. We move the decimal 1 spot over. It depends on which way you're going. So this is centi, this is milli. So if you're going from centi to milli, you go in the same direction. We move to the right. So if you wanted to convert, for example, centimeters into base units, meters, I want to turn centimeters into meters. I would go 1, 2. So 56 centimeters. There's an imaginary dot right there. I go 1, 2, and put the dot right here. So 56 centimeters would be equal to 0.56 meters. I moved over 1, 2 to go from centimeters to the base unit. Does that make sense? I usually don't, but I do want the 0 point. Also, when you're making a point, I don't know how many people I see do this. For example, 5.6. That's how I write 5.6. Can y'all see it? If y'all go up really close to the board, you will note the most tiniest of dots with no separation between the 5 and 6. I do not know how many papers I've received, and my test is if I can hold it at arm length, look at it, and I don't see it, after 1 second of trying, I count wrong. Your numbers should be legible. Because someone copying it down shouldn't be able to not see your period there. You should definitely make sure you have a period. And I just skipped a whole bunch of parts. So, for example, let's say we want to convert 7.25 liters into kiloliters. So we're at the base unit of L, so no prefix in front of the L. And we're going to know that we'll go over 1, 2, 3 times. So going from base L to KL, we go over 3 times. So 7.25. The point will move over 1, 2, 3. So it's equal to 0.00725. And I hate the fact that this PowerPoint actually shows the 0 being missing, because the numbers begin with 0 point if you're doing decimals. So, learning check. 1,000 meters is equal to which of the following? One 1,000 meters is equal to 1 millimeter, 1 kilometer, or yes, it would be a kilometer. So 1,000 is the Latin name for 1,000, Latin or Greek is kilo. So 1,000, 1 kilometer or kilometer. 0.001 grams is equal to what? It would be a milligram. 0.1 liters is equal to what? deciliter. By the way, it's deci. So this is your base or your U. They use the letter U for unit. Then this is deca, hecta, kilo, centa, and milli or milla. So that's deci. We use 10. We use decimals because we break the unit into 10 parts. The numbers into 10 parts. So what'd y'all say number 4 was? Oh wait, no, you have it down number 4. What is number 4? Yes. So you have to move over twice, so going from meters. Yeah, so there's a missing, so you could have put like unit meter, UM, but we never include the U. Yeah, it's not going from milli to something, that's meters. Do you know how I do unit conversion? Do y'all know scientific notation? So 0.01 meters. So I count how many spaces. That's 1, 2. So that's equal to 1 times 10 to the negative 2 meters. Negative 2 refers to centi. 10 to the negative 3 refers to milli. I'll put it right here. This is 10 to the negative 3. This is 10 to the negative 2. This is 10 to the negative 1. This is blank. It's 10 to the 0. This is 10 to the 1. This is 10 to the 2. This is 10 to the 3. Yes. So I would convert units into scientific notation and just memorize that 10 to the this can be replaced with the letter C. Alright, so we'll learn more about scientific notation later, but let's do 0.0056 meters. So I look at the period and I count between the first digit and the going to the after the first digit. So 1, 2, 3. So that'd be 5.6 times 10 to the negative 3 meters in scientific notation. Oh, sorry. So that'd be 5.6 times 10 to the negative 3 meters in scientific notation. I can replace the 10 to the negative 3 with milli. So it's 5.6 millimeters. Doing another example, 5,678 meters. Again, there is an invisible dot right there. If we're going and getting bigger, it's going to be positive. So I count 1, 2, 3. So that's 5.678 times 10 to the 3 meters in scientific notation. 10 to the 3 is kilo. Or times 3, 10 to the negative 3 is kilo. 5.678 kilometers. That's how I do it, but Miss England uses the, yeah. Which one? This one? This method? Ah. And that's why she uses it, is because it is helpful to some students. I look at the world in pure math. So let's say that I wanted to go backward. If I wanted to go backward, let's say I wanted the 5.6 millimeters to meters. So I put 5.6. I replace the m with 10 to the negative 3 meters. And then I can plug that into the calculator and see what it is. Or I can write down 5.6 and then realize that I need to move the decimal, put a lot of zeros in front of it. 3 spots. 1, 2, 3. So it should be 0.0056 meters. That's how I personally look at it. So when you use a measuring tool, is used to determine a quantity such as your height or weight. These numbers you attain are called measured numbers. A digit must be estimated. A digit that must be estimated is called uncertain. A measurement always has some degree of uncertainty. Record the certain digits and then the first uncertain digit. So, I really hate scientific notation, but it's used in science and you have to learn it because a lot of places do use it. How long would you say that line is in inches? 4 inches? So, would you put, let's see, 7.0325 inches? So, the only digit we're uncertain with the first digit. You should say it's roughly about 7 inches or something. First of all, use as an example. It is closer to 9. So then, how precise can you get with this ruler? So if you look, let me use centimeters actually. In this class we'll use centimeters. So looking at this, I see that I am very confident it's between 2 and 3. So I know it's 22 point something. I really can't see which line it is, so I'm going to estimate. 1, 2, 3, 3. It's I can't really tell if it's below 3 or greater than 3. This is where I'm uncertain. I don't know if that's supposed to be a 2, a 3, or a 4. I know it's somewhere around 3. I'm uncertain about this. So you write your 2 digits that you see, or are certain about, and you estimate 1 digit. That digit could be wrong, but it's going to be your uncertain amount. You make an estimate. Every time you record something, you're going to make an estimate. So I would say that is 22.3 centimeters. My point is what I wouldn't do is say that line is roughly 20 centimeters if I knew if it was precisely 22 point something. I also wouldn't write 22.310584 centimeters. This number implies I am absolutely 100% certain it's correct up to this point. Obviously, I'm not that good at measuring. But what this number states, 22.3 centimeters, is that I know it is around 22, and I estimated it is around 0.3. Does that make sense? I'm estimating this one digit. Whenever you write a number in science, this is going to be your estimate digit, where you estimate it. So that when someone else comes and looks at it, they would know that the correct answer could be somewhere between 22.2 and 22.4 centimeters. They know that it's roughly around that area. So if you see, for example, in chemistry, this requires 5.0003 grams. What that means is if you use 5.001 grams, you're off by that much. It could cause the experiment to fail. Or if you went and measured 5.1 grams. So it's a way for in science you can tell exactly how much you require or how much you measured. For if you recorded that the experiment used this much, you're telling when you write down your recording, I precisely knew that I used this many grams, and it led to this reaction. So graduated cylinders show each line represent 1 meter increments. This instrument is accurate to the ones place, therefore estimated digits should be in the tens place. For scaled instrument, the estimated digit must be determined by you. Liquid volume is 43.0 milliliters, not 43. Okay, so looking at this example. Basically, you can look at the tick marks. Remember that we measure from the meniscus, the bottom of the U-shaped or parabola of the liquid. So when you record an answer and you're looking at something, we know that the ones place, like 40, 41, 42, the ever line, we know that this thing is precise to the ones digit. Which means you need to estimate that the tens decimal place and the tenth place. If you were to write down your answer as exactly 43 milliliters, what you are telling whoever reads that after you is that you did not know precisely how much milliliters you used. You either used 42 or you used 44. But we can clearly look at this observation and know that it's somewhere very close to 43. Does that make sense? Likewise, if I put, this is the better example. Let me do it on a piece of paper. So if I did a graduated cylinder, and right here is 50 milliliters, and I wrote that this is 50 milliliters, what this number implies is that it's somewhere between 40 and 60 milliliters. Because the only certain digit right here is the 5. Does that make sense? And obviously, 40 and 60 is a very big range. what you would want to do is put that it was 50.0 milliliters. That is somewhere between 49 and 51 milliliters is where you recorded it. Or between 49.9 and 51.1. Be more precise. So we're trying to write how accurate your number is. All measurements will have some degree of uncertainty. When measurements are recorded correctly, it must be written with with a digit of uncertainty, an estimated digit, and a unit. The last digit in any measurement is a digit of uncertainty. It is the estimated digit. The digit you made a guess on. So let's talk about accuracy and precision. Accuracy first of all, do y'all know what the difference between accuracy and precision is? This is often very misused. A lot of people say things they're very accurate to something when they mean precise. And they say they're very precise when they mean accurate. So accuracy compares a measurement to a true value. So let's say that I have a bullseye. Am I very accurate? I am very accurate. No, I missed the target every time. Target was in the middle. So let's go over. So after today, you'll be able to say you're very accurate on a lot of things. So who is more accurate when measuring a book that has a true length of 17 centimeters? So looking at these numbers, so Susan is 17, 16, 18, 15. Difference between 15, our lowest measurement, and her height is 3 centimeters. So she's roughly around 3 centimeters of accuracy. Or precision, I should say. And Amy is 15.5, 15, 15.2, 15.3. Not a lot of variety in her amount. So who is more accurate? Susan, because her numbers are closer to the true value. Accuracy doesn't look at how much your numbers vary, but it's just how close they are. You can think of it, so going back to my drawing, if you notice, my points are all equally spaced around the true value here. They're all around it. Versus something like this. Nope, I'm hitting the same spot almost over and over and over again, but all the points are far away from the true goal. That's the distinction between accuracy and precision. So precision describes how closely your measurements are to each other, how carefully measurements were made. So out of these, you can see that the first set is the most precise. So looking at 0.2 and 0.4, it only varied by 0.2. The largest discrepancy. The second example, the smallest value was 17.9. The biggest number is 18.85. that's almost a full number off. And then the last one is even worse, going from 16.8 to 19.44. So if I were to ask who measured more precisely, Susan or Amy? Amy measured more precisely, but she's far off, but is more precise. We'd say Susan measured more accurately, but Amy measured more precisely. What we try to achieve in science is both accuracy and precision. If your numbers vary by a lot, even though it could be centered around the correct number, it kind of messes up the data because there's a large variety of possibilities. However, precision is you want to make your answers more precise. However, you don't want to make them too precise to the point where they're no longer representing the true value. It's a balancing game. So here, this one has high accuracy and high precision. This one still has high precision but low accuracy because it's far away. So, first image. How would you describe accuracy and precision? This would be kind of low accuracy and low precision. The numbers are too random, going everywhere. You can't really tell what the center of it is. What about the next one? Yeah, so it's far away from the true result, but they're very close together. And then the next one is going to be both high accuracy and high precision. You're hitting the mark, and all of them fall within the mark, so it's very precise. Alright, that's it for today. Did y'all all turn in y'all's homework?